Good evening, everybody. Thank you for joining us for our Caltech Astronomy Stargazing Lecture. I'm Dr. Cameron Hummels. I'll be your host for this evening's event. We are really close to the summer solstice, so it's still quite light outside, as the summer days go on, but we'll still be able to do telescopes tonight and stargazing after the presentation. The weather, as you can see, is quite clear, so it looks really good for the opportunities to look up into the heavens. We'll have probably 3 or 4 different telescopes set up looking at Venus is in the western sky, probably Venus and the moon for our solar system objects, as well as deep sky objects of the Hercules globular cluster and maybe the Whirlpool galaxy and so on and so forth. So it should be really fun. But let me give you a layout of what to expect for tonight. These events take place once a month on a Friday night, and in a few moments, I'll get through my announcements and I'll introduce our speaker who's going to talk all about the supposed emptiness of space and how we can reveal the structure that's out there and the material that's throughout these voids of space with these radio beacons. That presentation is going to last for about 30 minutes or so, and then we'll take a few questions for our speaker. Following that, you'll have an opportunity to make a choice. At that point, it'll be dark enough and the telescopes will be set up that you'll have the opportunity to go outside to the athletic fields that are right behind us here. And the way to get there is just to go out the front door and follow the signs onto the field. It's like less than a 2-minute walk from here. And at the same time as the telescopes are going on, we'll have a Q&A panel in this room. I'll set up a table and we'll have 4 panelists, our speaker, myself, and 2 other astrophysicists in the department to answer questions that you might have. It could pertain to questions relevant to the presentation content about the emptiness of space and what we're about to hear about, but it could also be questions unrelated to the content of the presentation. It could be a question that you have been thinking about for a while because you saw ancient aliens and you're really curious the veracity of those claims, or something you read about in the news, or something you saw on a telescope, or something related to astronomy or astrophysics or space science. And myself and our panelists will do our best to answer it from a scientific perspective. So both the telescopes as well as the Q&A panel in here will go until around 9:45 or so. And feel free to go back and forth. You might want to go outside to the telescopes first and see all the things that you can see. And then you're like, oh, I still got that question. So you can come back in here, or vice versa. As I mentioned, these events occur once a month on Friday nights. Our next one, I haven't yet set the date, but it'll probably be the middle of July. And I don't yet have a speaker, but it's probably going to be all about the newest addition to the NASA Space Telescope family, the Nancy Grace Roman telescope that's going to launch in less than 2 months now. And what's that? It almost got canceled. Fortunately, it did not get canceled. And it looks like it's going to launch, I think, the first few days in September. So there are many members of the Roman team that are at NASA Jet Propulsion Laboratory, as well as Caltech Astronomy. So I'm selecting from those members to come and give a presentation all about Roman and the science that will be done with this flagship telescope going into space in a couple short months. In addition to these events here at Caltech, we also have a sister series of events that takes place at a bar in Old Town, Pasadena, called the Astronomy on Tap series. These are, even though they're in a bar, they're open to all ages. Families can come. You just can't have the youth drinking alcohol, but everyone else everybody who's of age can do so. But it consists of 2 15 to 20-minute public level science presentations, much like we'll hear tonight, from different scientists, not just at Caltech, but also the Jet Propulsion Laboratory, Carnegie Observatories, UCLA, various different astronomy-facing institutions in Los Angeles. And there's also astronomy-themed pub trivia. There's telescopes. Sometimes there's live music. It's a lot of fun. We do them on Monday nights once a month. And our next one of those will be in a week and a half on July 6th, Monday, July 6th. I just set it up. I haven't yet advertised it, but the 2 speakers that night will be talking about tidal disruption events, when stars get too close to black holes and they get pulled apart and shredded by the gravitational potential of the black hole. And the other will be about the original discovery of galaxies by Edwin Hubble and collaborators from the Mount Wilson telescope about 100 years ago. So those should be really exciting, and I encourage people who are interested to come to that talk on Monday, July 6th. Other announcements. In addition to the events that we host here in Pasadena, we also collaborate with national parks around the American West to help host dark sky festivals. Because of course, we can go and set up telescopes here, but the light pollution of LA County makes it difficult to see as much of the sky and as many of the dark targets in the sky. So going to darker skies where there aren't a lot of cities and artificial lights nearby provides you with the opportunity to see more in the sky. And so coming up in September, there will be 2 dark sky festivals, one at Sequoia National Park, big trees, just a few hours north of here. September 10th to the 12th, if my dates are correct. The same weekend, if you can be in 2 places at once, I suggest this, Great Basin National Park in Nevada. You may not have heard of it. It's one of the less visited national parks, but it's actually pretty much the darkest sky national park in the lower 48 because it's so remote. It's about 7 or 8 hours drive from here, but the skies are really, really pristine. And so at these events, they're free. You have to pay to get into the park, or if you have a national parks pass, then it's free. But once you attend these, there will be star parties with lots of telescopes set up at them. There will be professional astronomers giving public talks, much like we'll hear tonight, and they're just a lot of fun. So we'll be helping with those, like I said, the second week in September, and we're also going to help with one at Lassen National Park in Northern California in August. I'll post all that information on our website in the next few weeks as things kind of converge on our participation in all of these sorts of things. I think those are all my announcements. So I'd like to introduce our speaker tonight. Our speaker grew up in the Bay Area in Northern California before attending Oberlin College in Ohio for her undergraduate studies, where she pursued an undergraduate degree in physics and was awarded it with high honors. Following that, she went to Cornell University in New York, and she pursued a master's and a PhD in astrophysics there, doing some really important work with respect to radio probes of the universe and some of the stuff that she's going to talk about tonight. She's a world expert in the field of using astrophysical probes to sense the matter distribution in voids through space. Through dispersion measure and other efforts. And she's going to talk about that tonight. So please welcome Dr. Stella Ocker.
Okay, thank you so much, Cameron, for putting on these incredible events. It's very exciting to be here with you all on a Friday night. So I'm going to start off by asking you to do a very simple exercise. I would like you all to picture the night sky in your mind. Okay, so now I'm going to make a wager. I suspect that most of you are imagining something that looks like this: a dark expanse punctuated by tiny pinpricks of light. Maybe you're a little bit more of an astronomy buff and you like to look at images from space. Okay, quick pause. At images from space. And you're imagining something that's a little more like this. So this is a beautiful image from the Gaia Space Telescope that shows the disk of our Milky Way stretching across the center of this image here. But regardless of the picture you have in your mind, I think most of us are probably imagining a night sky that is largely filled by starlight and nothing else. But the space between stars is not empty. In fact, this interstellar space contains all of the building blocks for the stars, the planets, all of the matter here on Earth that we are familiar with and hold dear. So these images that you see here, they only tell part of the story. And we as astronomers, we love to go out and search for things that are hidden to the naked eye. So what does interstellar space look like? Well, here's one example. This is the sky shining at a very particular wavelength of light, 656 nanometers to be exact. And this is the light that is produced by all of the gas that is between stars, that permeates the space between the stars that you see on the left-hand side. In fact, these two images are showing the same region of the sky. So why is this interstellar gas so important? Well, it actually plays a critical role in the life cycle of stars, and hence of our galaxy as a whole. So stars are born out of dense nebulae of interstellar gas. As they live out their lives, they grow, they heat the gas around them. Eventually, those stars die, and they either produce a supernova explosion or a planetary nebula, and eject most of their matter back into the interstellar medium, as we call it, where this whole cycle begins again. So this interstellar gas, or medium as I'll often call it, accounts for more than half of all of the ordinary matter in our galaxy. And as such, it serves as this important reservoir of fuel for ongoing star formation. But of course, this stellar life cycle is not happening in isolation. It occurs all over our galaxy, which itself sits in a network of other galaxies, each of which has their own interstellar gas with its own distinct properties and their own rates of star formation. And each of these galaxies is not sitting in emptiness either. All of the interstellar gas that is between stars, it has to come from somewhere, right? Where does it come from? Well, it comes from the space between galaxies, the so-called intergalactic medium, which it turns out is also filled with very diffuse gas. So you're starting to get the picture here. There's gas everywhere. So to illustrate this point, I'm going to play you a simulation that shows the formation of a single Milky Way-like galaxy. So this simulation was put together by a team of astrophysicists who used their best understanding of physics and computers in order to visualize all of the processes that go into galaxy formation. And this simulation that I will show you specifically shows the flow of gas from intergalactic space into a galaxy. So as the simulation progresses, we're now zooming out. So the original galaxy scale that we were looking at is at the very center of this video. This video is progressing forward in time. And you can see that gas is flowing from intergalactic space down into the very center of this young galaxy's disk. So the colors in this simulation correspond to the concentration of gas. The brighter the color, the more concentrated the gas is. And as time goes on, the gas at the very center of this galaxy becomes concentrated enough to start forming stars. Eventually, those stars die, they undergo supernovae, they eject gas out away from that young galaxy. Just now, we actually saw another galaxy come in and start to merge with the galaxy at the middle. And so what you can see in this video is that this process of galaxy formation is fundamentally cyclical. Gas flows in and gas flows out. And just to remind you of the sense of scale here, in the bottom right corner on the left side, so this here, you can see a rendition of the visible light from stars in this galaxy. So if you were to go out and look at the night sky with a nice telescope, you might just see this. But in reality, this disk of stars is actually surrounded by all of this other material. And critically, the formation of this galaxy and its life cycle is driven directly by material that's all the way out here, hundreds of thousands of light years away from the galaxy's center. So ultimately, we want to go out and empirically measure the properties of gas between stars and galaxies so that we can test our hypotheses for how galaxies and their stars evolve. But unfortunately, this gas is actually very hard to observe directly. And to explain this point, I need to introduce the concept of gas density. Right, so density describes how tightly particles are packed within a volume. In this simple cartoon, the gas density is increasing to the right. And broadly speaking, the denser the gas, the easier it is to see with our telescopes. A good analogy of this for you to think of is fog. The thicker fog is, the easier it is to see the fog itself. And in this case, we actually want to see the fog. The fog or the gas is the object of interest. Now, at this point, you might be wondering, wait, what about this image that you showed us? What about all of the light that is emitting from the gas between stars at 656 nanometers? Well, I have some interesting news. It turns out that the light in this image actually represents just a small fraction of all of the gas in our galaxy. This light that you see in this image, it actually corresponds to gas that is at a very narrow range of temperature and density. But we know that there must be much more gas out there that spans a very wide range of temperatures and densities. So just as with those previous images of starlight, this image again is just showing us a small sliver of the full picture of interstellar space. So many astronomers spend their careers trying to understand how is gas distributed between stars and galaxies? How does that gas evolve over cosmic time, or in other words, over the history of our universe? Also that we can slot one more piece of the puzzle in galaxy evolution. And I'm one of those astronomers. So here you can just see some of the telescopes that I use in order to collect data, in order to understand how gas is distributed in space. You can see that these telescopes come in all shapes and sizes. In fact, these upper two, they are so-called optical telescopes. So these telescopes operate at visible wavelengths of light, whereas the telescopes down here are radio telescopes. And just to make sure we're all on the same page here, I'll remind you that light covers a broad range of wavelengths. There's a whole so-called electromagnetic spectrum of light. And the light that we see here in this room, it actually corresponds to just one small part of this so-called spectrum. It corresponds to a narrow range of wavelengths of light. And most of the work that I'll share with you today actually corresponds to observations that are sensitive to radio light. So these are much, much longer wavelengths of light than the visible light that we see. Now, some of you might actually listen to the radio, and so you're familiar with this concept of tuning to different channels or stations, and those stations have numbers associated with them, something like 88.3 megahertz. And that actually corresponds to the frequency of radio waves that radio station is transmitting in. And in a very similar way, our radio telescopes are actually capable of tuning to specific frequencies of radio light from outer space. So these telescopes actually are capable of operating at frequencies that are similar to the frequencies that your own radios at home might receive. So unlike many other astronomers, I do not try to directly observe the light that comes from interstellar and intergalactic space. Instead, I use the cosmic version of a flashlight. So imagine, if you will, that you could point a flashlight in the direction of interstellar or intergalactic space. And as that light beam travels through the space, you see the gas illuminated along the way. Now, it turns out you don't need a flashlight because nature produces them for us, not in the form of visible light, but in the form of radio waves. So it turns out that every day across the entire sky, thousands of radio pulses are detected by our telescopes. This is just showing an animation of radio pulses arriving at radio telescopes in North America. And the actual arrival times are based on the real detections of these pulses. Now, what the heck are these radio pulses from outer space? Well, it turns out that they come primarily from two main types of astronomical sources. The first of these are called pulsars. So pulsars are rotating neutron stars. Neutron stars are the remnants of stars a little more massive than our sun. When those stars die, they leave behind this very, very dense core that gets spun up to very fast rotation periods. So pulsars emit radio beams that are actually offset from their spin axis. So they behave exactly like a lighthouse, as you can see in this video here. So this is showing the neutron star at the center and its radio beams spinning around. And here at the bottom, you can just see a rendition of the observed intensity of radio light from this spinning neutron star. So pulsars are very fascinating in their own right, and I encourage you to learn more about them in your own time. I'm not going to talk any more about what they are. Instead, I'm going to tell you about the other main source of radio flashes in the night sky, and these are called fast radio bursts, or FRBs. So FRBs also occur very rapidly. They only last about a millisecond, literally the blink of an eye. Unlike pulsars, which are mostly seen from our own galaxy, FRBs actually come from other galaxies. So they come from much further away. They're also much brighter than pulsars. So they can be up to over 10,000 times brighter than most of the pulsars we see from our own Milky Way. The key distinction between FRBs and pulsars for the purposes of this talk is that FRBs occur randomly. So we typically do not see an FRB coming from the same exact position on the sky more than once. Pulsars are by their very nature periodic sources. We see their radio pulsations very regularly. So this is just showing an artist's rendition of a fast radio burst. Unfortunately, we don't actually know what produces FRBs. It turns out that also does not matter for the purposes of this talk. If you would like to learn more about this mysterious phenomenon, I encourage you to check out another stargazing lecture that was given a while back by Liam Connor about this subject. But broadly speaking, we see these flashes arrive at our radio telescopes all the time. And why am I telling you about these radio sources if I don't actually care what they are? Well, it turns out that they behave, as I said, like a cosmic flashlight. It turns out that as these radio pulses and bursts travel through the space between us and the source, their radio signal is actually distorted by the intervening gas. So how does this actually work? Well, one of the main ways is that we see radio pulses are slowed down by the gas that is along the pulse's journey. So here I'll just show you, this is a very simplistic cartoon of what the signals we look at actually are. So we see a pulse as a function of time. So this is the actual pulsation in radio waves. And we can actually, before that, yeah, so this is the radio pulse, and this is just static noise, which is typically a part of every signal we look at. And we can see the effects of intervening gas by actually tuning our radio telescope to different frequency channels along the lines of what I was saying earlier. So we can actually examine how the burst behaves for different frequencies of light. And it turns out that we see that lower frequency channels or components of the burst arrive later in time than higher frequency components. And this frequency dependent time delay, it actually depends directly on the total gas density along the line of sight to the source of this radio burst. So you can see this illustrated in this cartoon. So here, the blue colors represent higher frequencies of radio waves, and the red corresponds to lower frequencies of radio waves. And so the blue arrives at the Earth before the red. The other main class of propagation effect, as I'll call it, or the distortion that we see in these radio signals, is that the pulses are actually bent by gas along the line of sight. So the radio pulses do not travel in a straight path from the source to the observer. And this is actually exactly the same physics as the refraction that you might be familiar with when you put a spoon or a pencil in a glass of water. So you see that refraction of light causes the appearance of the spoon to look bent or disjoint exactly at the interface between air and water, which have two very different compositions and densities. We see this exact same effect with radio signals that travel through space. And it turns out that because this bending depends on where the material is changing significantly in properties, this actually allows us to use these radio signals to study changes in the density of gas along the line of sight. So we can pinpoint, this radio pulse actually saw a change in the gas density at this particular location. Right, so this is the main point of the talk. If you take away nothing else, it should be this, that pulsars and FRBs behave like radio beacons, and we can actually use these as backlights because the distortions of these radio signals reveal how gas is distributed, both between stars, but also between galaxies. Right, so for the rest of this talk, I'm just going to take you through two key science cases that we use these radio sources for. And the first of these is to study the interstellar gas in our own Milky Way galaxy. So here you are looking at the all-sky distribution of known pulsars. And to orient the viewer, here you can see that in this image, we are seeing the so-called galactic plane. This is the disk of our galaxy where most of the stars reside. It stretches across the center of this image. The galactic center is over here, so this is looking towards the very center of our galaxy. And one of the things you'll notice is that these pulsars are not uniformly distributed on the sky. In addition to them primarily being concentrated in the galactic plane, you'll also notice there seems to be some asymmetry in their distribution. There seem to be many more pulsars right here in particular, and that is actually entirely due to observational bias. We had some telescopes that happened to search for pulsars in this particular region of the sky for much longer than these other parts. So that's why we see more here. But this is a key point, is that we actually expect there to be many more pulsars that are not shown here, that are yet to be discovered because we have not searched all parts of the sky evenly. You'll also notice these two clumps down here. These are actually the large and small Magellanic Clouds. These are small satellite galaxies that orbit our own Milky Way. And these are actually the furthest known pulsars to date. So we can use all of these pulsars distributed across the sky, study the distortions of all of their radio signals in order to try to build up a map of how gas is distributed within our galaxy. I'm going to show you one example of how we try to do this in a region of space that is fairly close to the Earth. So in this video, you are seeing essentially a modeled rendition of pulsar sight lines and the material along them. So these spokes each correspond to an individual pulsar. And then these blobs, these are models of structures in interstellar space. These little black squares, they correspond to specific regions that we identified as being of interest along each pulsar line of sight. So we try to collate all of this different data from all of these different sight lines in order to build up a three-dimensional picture of how the gas is distributed. And one of the benefits of working with computers is that you can actually manipulate these models in 3D, right? You can zoom in and out and you can turn them around and really try to understand what's going on. So we actually did this on much larger scales using much more data in order to construct a new model for the density structure of the Milky Way. We call this model NE 2025. The reason of the name is that NE stands for electron density. That is the particular physical property that we were trying to constrain. 2025 is just the year through which we had data in order to constrain this model. And what you're seeing here is a projection of the model looking down onto the galactic plane in this fictional scenario where we could zoom out and look at our own galaxy from above. And so here the Earth is at this black circle here. The center of our galaxy is here. And all of these structures that you see as most prominent are the spiral arms of our galaxy. So these colors, they are actually representing, again, the concentration of gas, the gas density. So brighter colors mean more dense gas. And one of the things that you'll notice is that this model, it looks quite fuzzy. And there are a few reasons for this. One of them is that we don't have very much data to constrain this model. right? So a lot of the most constraining pulsars that we used to build up this model are shown here. And you can see they all seem to lie in one part of the galaxy, which again is due to observational bias, where we've been pointing our telescopes. So this is a model, it has to extrapolate. So basically we extrapolate from all of our data over here to try to predict what things look like over here. But I'm willing to bet that this is wrong. And there's a famous saying in science, all models are wrong, some are useful. I would argue this is still a very useful model. We can use it for many different things. We can actually use it to predict the distances to pulsars. We can use it to correct the distortions that I was telling you about. Some people don't like those distortions from intervening gas. They actually think that's noise and a nuisance. It's my signal, so I love it, but some people want to remove it and they can actually use this model to do so. But nonetheless, there are significant problems with this modeling effort. And the key limitation, of course, is just the data that we were able to use to constrain it. So how do we get around this? Well, one great way is to use FRBs. So as I said, FRBs are fast radio bursts. They come from other galaxies. So we can use them to try to fill in the gaps that the pulsars are not able to fill in our model. So here now you are seeing again the pulsars in blue, and now you can see the distribution of known fast radio bursts in red. And you can see they span a much broader expanse on the sky. This is because they come from other galaxies, right? And so we see them happen all over the sky. They are not concentrated in the galactic plane because they do not come from our galaxy. But of course, there are still, again, some concentrations, again, because of where our most sensitive telescopes are able to detect these FRBs. But you can start to see that because there are so many, and they come from all parts of the sky, they can really help us fill in critical missing information about the structure of our galaxy. And so that's precisely what we are attempting to do moving forward, is to combine our knowledge of pulsar signals within our galaxy with data covering FRBs from outside our galaxy to fill in our understanding of everything in between. Now, there's just one complication with this. Well, probably more than one, but the one I'll focus on is that these sources, they come from very far away. So we're not just viewing them through our Milky Way, we're viewing them through everything in between us and the galaxy they came from. And I want to just take a moment here to appreciate the serendipity of detecting a fast radio burst, right? So many fast radio bursts have to travel billions of years to arrive at Earth, but they only last a millisecond. So they take this long and then they just come and go in the blink of an eye. But even within that millisecond of data, we're actually able to recover information about its entire journey here. And this is, again, without even knowing what they are. So the trick to using FRBs to understand gas within our galaxy, as well as gas between other galaxies, is to try to disentangle all of these different regions along the fast radio burst journey to us, right? So the FRB is affected by gas not only in the Milky Way, but also its own galaxy that it came from, potentially other galaxies along the line of sight, as well as all of the gas that is between these galaxies. So how do we get around this problem? Well, we use FRBs that are located at different distances. So we try to detect some FRBs that are close by, some that are midway, some that are further away. And in this sense, we can build up a map of how gas is distributed across cosmic time. So the idea is that sources that are closer to us, FRBs that come from more nearby, they will have lower total gas densities that we detect. The sources that are further away will have larger total gas densities. And so the amount of material that is in between us and the source is directly related to the distance. And in this way, we can try to build up a picture of not only the gas between galaxies, but also potentially within our own. So many teams around the world have been working to make this type of science possible. And I'm part of a team here at Caltech that uses a telescope called the DSA-110. So you can see the DSA-110 here. This is an array of radio dishes at the Owens Valley Radio Observatory up near Bishop, just a few hours away. And this telescope is really special because it was purpose-built to detect FRBs and use them for exactly the science that I've discussed. So this is a team effort. You can see just some of the people here at Caltech and some who have now moved on from Caltech who have contributed to this, Vikram Ravi being the key leader of this whole project. And of course, there are also many more people involved in this project that I'm not even showing on this slide, including many staff and engineers at Owens Valley Radio Observatory. So what has DSA-110 done so far? Well, it's detected almost 100 FRBs to date. About 70 of them have host galaxy associations. So we actually pinpointed the FRB and the galaxy where it came from. And here in this artist picture, you can actually see a composite of all of the different galaxies that we saw FRBs coming from in this really nice work that was led by grad student Kriti Sharma here. Now, the nice thing is that these FRBs, they come from galaxies spanning a huge range of cosmic time. So some of them come from very nearby, some of them come from over 1 billion light years away. So in particular, the FRBs that come from very, very nearby galaxies are great for me personally because they tell me a lot about the Milky Way. These are two nice examples. So this FRB up here, it comes from a galaxy that is about 200 million light years away. This FRB down here, it actually came from an even closer galaxy, about 12 million light years away. And these two cases are really great because they are so close that they tell us quite a bit about both the Milky Way and its neighborhood. So they tell us a lot about how gas is distributed just within the local environment of our galaxy. But these are just two of the most nearby examples. Eventually, we want many, many more FRBs in nearby galaxies. Right, so this is a really exciting time to be working in this field. Today, we know of about 4,500 pulsars within our own galaxy, and we know of about 4,000 FRBs, mostly coming from outside our galaxy. But we expect the situation to look very different in less than 10 years. So by 2034, we are anticipating about 20,000 known pulsars that will mostly be discovered by upcoming telescopes and more than 100,000 new FRBs that will be discovered. And what is going to enable this amazing transformation, you might ask? Well, it's going to largely be enabled by this deep synoptic array. So this is actually the successor to the DSA-110. Some of you might have been at the stargazing lecture given by the PI, Greg Hallinan, back in November. If you want to learn more about this incredible telescope, I encourage you to check out the recording of this lecture on YouTube. But the short gist of it is that this is expected to be the most sensitive radio telescope in the world, particularly for finding new pulsars and FRBs. So this is going to be an array of radio dishes built in rural Nevada, and it's going to start construction next year, and we are expecting to start taking data with it in 2029. This is going to be especially amazing for studying our own Milky Way, because the Deep Synoptic Array is going to be doing an all-sky survey that repeatedly visits the same regions of the sky. So we're going to have very deep observations looking through various parts of our galaxy, and we're going to revisit those sections again and again and again. And in this way, we can build up very, very deep observations with a lot of sensitivity to pulsars that are in regions of our galaxy we haven't even seen before. So with that, I just want to remind you, pulsars and FRBs are radio beacons. They're fantastic tools because their signals reveal how gas is distributed between stars and galaxies. And we expect that in the next few years, new telescopes like the DSA are going to reveal our own Milky Way in never before seen detail. Thank you.
we can take some questions of our speaker. Raise your hand and I'll get to you. And oh, now I have to step on people. Pardon me, guys.
Yeah, question, where did the gas come from? Was that from the Big Bang or from other stars dying? And
Yeah, so everything comes from the Big Bang ultimately, but the gas properties, they change a lot over the history of our universe. Most of the gas that I've talked about today, it primarily arises within the past couple billion years of our universe, and it is very strongly affected by local star formation and stars dying within the last few million years. So that gives you a sense of this is a constantly evolving process. And the gas, sometimes it's going into stars. Now that same matter is inside a star, but eventually those stars die. They eject their matter back out into interstellar space. And so it's this constant dynamically changing system.
Yeah. Oh, wait, there's one to my left. Oh.
Thank you. Very cool talk. Thank you. I have a question about sort of narrowing down the exact density distribution. So I think you talked about one of the challenges is that the FRB signals are inherently line integrated along the line of sight. I guess one of the solutions that you mentioned is detecting multiple FRBs along that line. But even with the closest one, is it true that there's sort of like a non-unique solution where the phase differences between the different frequencies can either be from like a very sharply peaked area of density, or they can accumulate across like a longer stretched out low density region? If that is the case, how do we further deconvolve that distribution?
Yeah, that's an excellent question. There are many sophisticated techniques that have been developed to tackle the precise problem that you've posed. And in particular, the effect that I talked about where radio pulses are bent by material along the line of sight, the refraction, it turns out that we actually see a very rich phenomenology of such effects, even beyond simple bending of the light, but we also see diffraction. So we actually see the light split apart into multiple paths. And there are a number of different ways of studying those particular propagation effects. And it turns out that the fundamental physics, the optics of how that light travels, it depends very sensitively on the density distribution. And in particular, by observing multiple different types of these effects, refraction and diffraction, they help us precisely with this degeneracy that you've described.
Another question in the middle. Can you pass it down?
Thank you. All right, got me a quick question, hopefully. Most of this is on density, but are you also thinking about a composition of the gas? I mean, assuming most of it's hydrogen, but what does the future look like in terms of actual composition?
Yeah, that's an excellent question. So I really brushed this under the rug, but all of the radio distortions that I talked about, the propagation effects, they're actually only sensitive to electrons, free electrons, in fact. So they primarily tell us about hydrogen. But in fact, most of the gas that I've talked about, it is hydrogen and helium. And the other types of chemical compositions of gas that you can find in interstellar space, they constitute actually a very small fraction of all of the gas that intervenes. And so for our purposes, we don't worry so much about chemical composition. We're really just worried about the bulk volume of the gas, which is mostly hydrogen and free electrons. But there are many other astronomers who care very deeply about chemical composition, and they make it their whole lives to study it because it does, in fact, tell you other key parts of this whole puzzle.
We can take one more question. Don't worry, there will be opportunities for more questions during our Q&A panel, which will last a lot longer. But there was a question up here.
You said one more question. This one's two, but it's quick. Don't worry.
Just make it one.
Of course. Oh, okay. Well, it's going to be hard. These fast radio burst emitting galaxies, do we know how far they are away?
Yes. So for a small number of cases, nearly 100 or so now, we actually are able to measure the exact distance to the galaxy that it came from. And that actually requires typically following up observations of that galaxy with optical telescopes in order to detect other signatures that are sensitive specifically to the distance.
Thank you.
Okay, let's. No, but then our online audience can only hear through the mic. If you stick around during the Q&A panel, there'll be like an hour and 15 minutes worth of question asking time. Let's thank our speaker again. So as I said, now is the kind of choose your own adventure portion of the evening. We're going to have a brief intermission in here as we set up the table, and then we'll have a Q&A panel that goes for the next hour and 15 minutes. So if you didn't get your question asked, stick around and ask it of our panel composed of the speaker, myself, and 2 other astrophysicists in the department. But we also have the telescope set up. I'm told they're pointed at Venus, the moon, and I don't yet know what the other 2 the digital electronic telescopes are pointed at. But if you follow the signs out the front door and around to the athletic fields behind us, you'll be able to look through the telescopes, and those will be operating for about an hour. So feel free to come back and forth between the 2. And Astronomy on Tap, July 6th, Monday, July 6th. Okay, we'll get set with the rest of this in just a moment. All right. Thank you guys for sticking around for our Q&A panel. So what we'll do now is each of us will go through and introduce who we are and what our scientific research is, so you have an idea of what our specialties are. Again, you're free to ask whatever questions you have about astrophysics or related space science, and we'll do our best to respond and give a reasonable explanation. But obviously, we know more about the stuff that we actually work on. And so if you know what we're working on, it might help you to guide the questions in those areas. So I'm Cameron Hummels. I am a research scientist here. I'm also the director of astrophysics outreach, putting these events on. My research mostly pertains, actually it pertains to some degree to what Stella was talking about. I do a lot of computational modeling of galaxies, but also the low density material, like Stella was indicating, could be studied with these radio sources. So the intergalactic medium, that's the stuff in between galaxies, the circumgalactic medium, which is the low density stuff around galaxies, and to some extent the interstellar medium, the higher density stuff between stars within galaxies.
I'm Jeffrey Moe. I'm a postdoc at Caltech here and also at the Carnegie Observatories like Stella. I'm interested in binary stars, especially the ones that are in binaries with stars that are dead, like white dwarfs, neutron stars, and black holes. I'm also particularly interested in when they explode and merge in light and in gravitational waves. I'm also involved with building instruments so that we can find more ways to observe these things.
I'm Caitlin Shen. I'm a postdoc here at Caltech. Fast radio bursts, which for Stella is a tool, is for me my main scientific research area. And so I'm what you could call an FRB generalist. I help build and operate radio telescopes to try and find all these FRBs. I try and understand where they come from and how they're distributed in space. And I'm also involved in following up the host galaxies of some of these FRBs that we are able to localize.
I'm Stella.
Okay, we can take questions from the audience, and we have our online audience as well. We're live streaming this on YouTube, so we'll periodically ask questions that they've been asking as well.
Hi, I was wondering, in Stella's case, mapping the galaxy, do you make use of any of the 21 centimeter line that measures density of neutral hydrogen in the galactic plane, et cetera? I've seen some beautiful maps of artist renditions, of course, but making use of that data. I was wondering how that informs your own maps.
That's a great question. So the 21 centimeter observations indirectly inform my work, in particular to the extent that they tell us about the spiral structure of our galaxy. But I do not make explicit use of 21 centimeter observations directly in virtually any of my work. And that's mostly because I'm less interested in the neutral hydrogen and more interested in the ionized hydrogen, the hydrogen that is free of its electrons. But I think that all of these different parts of the interstellar medium, they're all very intimately related to each other. And so one of the things that we try to do as astronomers is we try to talk to other people. So I try to talk to other astronomers who look at 21 centimeter observations so that we can try to understand how our work connects with each other into the bigger picture.
And I should just add, there are those of us in the computational community that care deeply about the connection between how much of that hydrogen is out there that's neutral, like you can study with 21 centimeter emission, as well as the component that's ionized, so that you can get the aggregate amount of mass that's out there, not just the stuff that's ionized and not just the stuff that's neutral, but you can see the bigger picture of everything together. Because it puts a lot of constraints on cosmological models, it puts a lot of constraints on galaxy evolution models, it puts a lot of constraints on a variety of different areas of astrophysics to measure that full bulk mass content. Okay, additional questions. The young gentleman, as always, has, I'm sure, a very hard question.
If we can measure the length to the galaxy that the FRB came from, is that how we discover galaxies?
Yeah, that's a great question. So that's not how we discover galaxies, but there's so many galaxies out there in the sky that we know probably that the FRBs come from a galaxy. And so when we're able to localize an FRB to a particular galaxy and then follow it up with optical instruments like visible wavelength instruments, it's possible that we are studying that particular galaxy for the very first time because there's billions of galaxies out there and there's not enough resources to look at all of them individually. And so in that way, we are kind of like discovering a galaxy for the first time because we're really studying it.
Good question.
Hello. So you mentioned during the talk about the like refraction as the light goes through the various mediums. Do you have to deal with gravitational lensing on top of that? And if so, do those two things kind of mess with your measurements of like where those galaxies or like where the FRB is coming from, or you know where the pulsar is in space?
So gravitational lensing does happen, we think, although we haven't actually detected it towards any of the examples that I showed, any of the FRBs or pulsars. So while it in theory could happen, it turns out to be really, really hard to detect. And one of the main reasons it's hard to detect is precisely because the lensing signatures are somewhat degenerate with the distortions from the gas from things like refraction and scattering. So that's one of the key challenges, especially for people who have really dedicated their lives to trying to make a gravitational lensing detection happen, is that they have to try to contend with all of the propagation effects that I talked about, which for them are really a headache. But we hope that in the future, like with instruments like DSA, that we will detect so many FRBs that the sample will be large enough that even a very rare occurrence of a gravitational lensing event will be detectable.
All right, I promised this guy next spot.
All right, thank you so much for the presentation. I've got like a couple questions. So first of all is, because we are using radios to listen into pulses, FRV pulses and pulsar radio frequencies, because it's like light years, thousands of light years away, and by the time I assume by the time they get there, it's like very small. So like how big or how sensitive does the telescopes are needed to actually listen or to receive the radio frequencies? And second of all is that how are we I've seen the map of our galaxy with the gas, and I'm curious on like how we're able to map the gas densities and know where we are in the galaxy if we're not able to go out and see our galaxy from a top-down view. And how are we able to triangulate the how are we able to triangulate our findings if we can't exit Earth's or the solar system and to triangulate where the stars and the things are?
I'll do the second question first and then go back to your first question. So one of the things that we have to do when we're trying to model our galaxy in 3D is we have to make some assumptions, for example, about whether it's symmetric in certain directions or not. And we try to use as many sightlines as possible where we know the exact distance to the pulsar. So we have pulsars that are distributed across many different parts of the galaxy. They all have their own known distance. And so because there's this relationship between how the gas is distributed along the line of sight to that pulsar and where it is located, you can try to essentially use that 3D distribution of pulsars to build up that 3D map. And so that gets around some of the problems that you discussed, but there is always this issue of we don't understand, for example, the spiral arm structure of our galaxy very well, precisely because it's very difficult to infer just from our position here on Earth. And so we do have to make some assumptions about the spiral arm structure based on our best understanding of the data that exists, but there will always be uncertainties, and we try to acknowledge and account for those uncertainties whenever we use this type of 3D model of our galaxy for other purposes. Okay, and then the first question was about how sensitive do the radio telescopes need to be to see these pulsations? So I'll let Caitlin fill in any gaps of what I say, but you don't actually need a very large dish. I think you can actually detect a pulsar, especially the brightest ones, with something as small as this table here. I don't know if you want to add anything.
Yeah, so pulsars, because they're in our galaxy, and the brightest pulsars, as Stella mentioned, we're able to detect with fairly unsophisticated relative to state-of-the-art like DSA technologies. But FRBs, because they come from so far away, like from the first few billion years of the universe even, we do need more sensitive instruments to find those. And the reason why we can see FRBs from so far away but not pulsars is because FRBs are so energetic, and that helps us in trying to detect them even if our sensitivity isn't the best. And so it's hard to give an exact number without being too jargony, for example, but I'll just put it out there that radio, the more sensitive you want to be, the bigger essentially you want a dish or a collecting area or just a bucket for photons for light. And another cool thing about things like the deep synoptic array is that instead of having one gigantic 500-meter dish, which is a really, really big size and also the size of the largest radio telescope in China, you can have a bunch of smaller dishes, say 1,650 6-meter dishes like the DSA is having. And then you can sort of more or less add up all the signal in all these different dishes to sort of get around the problem of having one big dish. So that technique is called interferometry, and that's another way that we can help our radio telescopes be more sensitive to these really distant signals.
Okay, question back here.
Hi, layperson here, and I have a lot of questions, but the new deep synoptic array, how is it different than the last version? And can we use the last version, since there's going to be a new one, to just spend more time going around to try to, see other parts and so we don't have to extrapolate about what's going on in the other regions that aren't stared at, and the extrapolations don't seem to work, but there's humor in that. I didn't find it, but I know it's in there somewhere. Gosh. I have that's enough.
We'll come back for subsequent questions.
Yeah, so that's a great question. Astronomers, it's a little running joke in the field that astronomers are terrible at naming objects and instruments. For example, there was this instrument that's called the Very Large Array. And so the Deep Synoptic Array is not a complete identical successor to the DSA 110. Actually, a lot of the technology is going to be completely different. And so the DSA 110, which is in California, is pretty much custom built to detect FRBs. But the Deep Synoptic Array that's going to be in Nevada is basically going to take pictures of the entire radio sky. And so it's going to do a lot more than just FRBs. It's going to look at the faintest galaxies that we can see in the radio light. It will look for other explosive transient events. It will try and help, it'll let us try and understand the nature of say, dark matter through how this diffuse gas that the deep synoptic array is able to image will be able to do that. And I think sort of disentangled, you also mentioned if the DSA can look at different parts of the sky than the DSA 110, and if that will help with extrapolation. So the extrapolation part, probably not, because it's just fundamentally difficult to be able to observe past the other side of the galaxy from where we are. So even having 2 telescopes is not enough. There's other challenges associated with that. But the DSA, the Deep Synoptic Array, and the DSA 110 will be operating as different instruments, and so they probably will be looking at different parts of the sky and finding different things.
One sec, there's 2 questions. There's a few questions online that I've promised the people that I will ask our panel so they aren't left out cold. One is, are there radio telescopes or radio arrays like the DSA 110 or the DSA telescope that are in the southern hemisphere? Or is it only just the ones that are in the United States?
The southern hemisphere has some of the best radio telescopes in the world. There's a lot of radio telescopes in Australia. There's I don't remember their full names, but there's ASCAP, there's Parkes, there's Meerkat in South Africa. So there's a rich history of radio astronomy, especially in Australia, but also in the Southern Hemisphere. And in fact, one of the biggest, most exciting next generation radio telescopes that is coming online, besides the Deep Synoptic Array, is something called the Square Kilometer Array, or the SKA, and that is also entirely in the Southern Hemisphere, with sites at Australia and South Africa.
Excellent. One other question from the online audience is, from the perspective of intergalactic plasma, is the universe homogeneous and isotropic? Is it uniform in its distribution roughly? And does it have, is there more on this side of us in this direction of the universe, or more on that side, or is it generally kind of the same? And I think this question bears out from the observations of the cosmic microwave background, that for the most part, the radiation that we're seeing that's left over from the Big Bang is kind of the same in all the directions and isn't focused more in that direction than it is in that direction. So the question was basically about the IGM, the intergalactic, the IGM. Well, I figured I'd let you. You're the big player tonight. I'll chime in where I can.
Yeah. So, I mean, I think if you could zoom out on the kind of biggest scales, the intergalactic medium would mostly look homogeneous and isotropic. But a lot of the really interesting physics is happening at smaller scales where it actually does not look homogeneous. So, for example, we know that the Milky Way sits inside a local group of galaxies. So the intergalactic medium that is directly around our own galaxy and its group is enhanced in density with respect to other regions. And we also see other very large clusters of galaxies that reside in what we call filaments. So these are parts of the so-called cosmic web. These are regions where the intergalactic medium is much denser, where most of the galaxies are concentrated. Between different filaments of the cosmic web, there are voids where the intergalactic medium is much less dense. And so when you look on those kinds of scales of filaments and connections between galaxies, it really does not look homogeneous at all.
I 100% agree. The only thing I'd add to it is an analogy. If you're in the middle of a forest and you look around you, you could, let's just say you're in the middle of a really big forest, let's say Sequoia, and you ask yourself, what's the density of stuff like trees in that direction versus that direction? It's on large scales, as you were saying, it's probably pretty much the same in all directions. But once you start zooming in on specific things like the density of matter through the trunk of a tree is much higher than the density of matter in the gaps between the trees. So on those smaller scales, like the scales of a galaxy or a star, that definitely there's variation there. But for the most part, absolutely. The general gist of it, there's about the same amount of stuff that's homogeneous over here as there is over here. Okay. I'll go back to the young gentleman because I know it's approaching your bedtime and you probably have to take off.
Does dark matter also distort the radio waves? And
Does dark matter also distort radio waves? Who wants to talk about, yeah, gravitational lensing?
So this is actually a really, really active question of research that no one exactly knows the answer to. So you just asked a very good question. And this relates to one of the coolest possible applications of fast radio bursts that I'm personally a fan of, which is something that also relates to another question that someone asked, which is the lensing of FRBs. So it turns out that if dark matter takes a certain kind of form, say if it consists or if it's comprised of like something called primordial black holes, like tiny black holes from the very, very start of the universe. And they occupy like a small mass range, or they're like, you know, certain sizes. It turns out that the signal of FRBs, if it happens to intersect one of these hypothetical dark matter objects, it can result in like a very, very, very small lensing signal or like a very small time delay. And we call that nano lensing. So it's different than like, this is very jargony, I'm sorry, but it's different than when you look at a pretty picture of a lensed galaxy and you see multiple images of the same galaxy around a lens. That's called a strong lensing signal because there's a really, really big lens, which is a really, really big foreground galaxy or galaxy cluster. So what I'm talking here is something that is on the scale of like nanoseconds and the associated time delay with that. So very small and very cool.
Things I learned today. I've never heard nano lensing before. All right.
How are y'all doing today? My name is Malusini Aleka. I'm a rising sophomore at Howard University and a member of the 9th cohort of the Karsham Scholars Program. Earlier this week, I attended the seminar given by Katie Bowman about how she took the first picture of the black hole. And she mentioned that the position of the telescopes do matter on the Earth. And the number of telescopes that we also have also matters as well. So considering there's a limited amount of telescopes in a limited amount of areas on the planet, do you think that the fast radio bursts that we're getting or like the images that we're able to project from space are more sporadic, or do they all work together to like synchronize and we can pinpoint that exact period of time? Or does it just come down to approximation?
Everyone's asking such fun and great questions today. So Katie Bowman was probably talking about in the context of the Event Horizon Telescope. So earlier I mentioned interferometry, where you have multiple different sort of buckets of light. The Event Horizon to like find a signal, the Event Horizon Telescope takes this to the extreme where they essentially like coordinate like 7 to 12 telescopes all over the world and have them point at the same part of the sky at the same exact time, effectively turning the entire planet into one collecting bucket for photons, which is crazy. It blows my mind, but it works and it's amazing. Now, compared to that, we have interferometry on a much smaller scale for FRBs. So this other like radio detection telescope that I'm a part of, what it does is it kind of turns the baseline of North America into a similar sort of like big bucket. And the reason why the configuration and the like lengths of the detection, or sorry, the like length in between these telescopes and where these telescopes are positioned, it matters for our ability to be able to precisely localize a particular signal in space. And so just like spatially. So if we only have 2 baselines, for example, we can't triangulate the signal. If we have 3 baselines, but they're not super far away, then we don't have like small precision. Our localization will be like less precise. So in that sense, we can have certain instruments that work together in specific configurations. And if you have those specific configurations met, then you can localize these fast radio bursts to very, very small regions on the sky.
Right. Some people in the back here.
Hello, my name is Myra. My background is definitely not in the amazing things that you guys do. So I was just wondering, with all of this like mappings and like data and discoveries, where does this really take humanity, or like what are the opportunities for humanity's advancements with all of these discoveries? Oh, and is the plot to Interstellar real?
You're giving me the hard question about.
So what are the benefits to humanity for what we're doing here? I think about this a lot. No, I want you to answer. I'll chime in after.
Okay. That's a good question. I think since humans have been around, we've always been trying to figure out where we come from. So I think what mapping kind of where we are in the galaxy and where and what's around and outside the galaxy, I think is kind of part of that tradition. What else? What else is?
I'm interested to hear what you have to say. I mean, absolutely, I agree that pure research is justified. Doing things for curiosity's sake, to try and understand our origins, our cosmic origins, is extremely important. Trying to understand why the world, not just our world, but the universe looks and behaves the way that it does is important for just understanding how nature works. But in terms of direct application, I think there are three particular things where there's direct application from astrophysics onto our everyday life. One is asteroid impact. So we're not talking about it here, but one of the things that astrophysicists do is track asteroids, and some of those asteroids have a probability of running into the Earth. Everyone's seen Deep Impact, everyone's seen Armageddon. What's the other one? Don't Look Up, that came out a couple of years ago. These are, you know, somewhat farcical, but the ideas behind them are true. There could be space rocks that are going to hit the Earth, and what do we do? Because it could be a big problem. And so there are many teams, some of them here at Caltech. There's a new telescope going up from NASA in the next few years called the NEO Surveyor, that is going to map and search for various different potential objects that might run into the Earth and identify them before it's too late. And then there's other work to do to redirect those things so that they don't run into the Earth and they don't cause both loss of life as well as catastrophe here. So I think that is a direct application of astrophysics, doing this sort of work. Another area in which we could find benefits and direct application is if there's the discovery of life off of the Earth. You know, not only is that potentially the most important scientific discovery ever, it has impacts in religion, in philosophy, in biology, in all manners of science that could change how we see our place in the universe. We haven't yet done it, but there's the possibility, the real possibility, that we're able to do it. Programs like SETI, the Search for Extraterrestrial Intelligence, and all of the exoplanet work that's been going on over the last 20 years is making really, really amazing advances in that area. So that's one area. And then finally, you've probably heard the term dark energy. Dark energy is a nebulous concept that we don't well understand really from cosmology, that's driving the expansion of the universe and driving the acceleration of the expansion of the universe. And as we are able to better understand the nature of that driving energy, it might provide opportunities for us to extract energy locally so that we don't have to rely on solar panels or burning coal or other kind of traditional means for generating energy here. So the Department of Energy, the US Department of Energy, is actually investing money into research in astrophysics for this reason. Not only because it's important to just understand why nature behaves the way that it does, but it might also have an application that could benefit people like everyday Americans, instead of just those of us who really get into astronomy and physics and want to study it in school.
The plot of Interstellar.
Oh yeah, the plot of Interstellar. Yeah, I forgot that part.
So rehash Yeah.
Spoilers.
Spoiler. If you haven't seen this movie, great movie. Great movie. Earth runs out of food. They send a team of people to go scout out other planets. They don't come
But
back.
other planets outside of our
Outside of our solar
because there's a
system.
wormhole out by Jupiter that they
Right.
can go through.
Yeah. Then
There isn't, I mean, in reality, no, this isn't true. There's no wormhole that we know about in our solar system
yeah.
or in the universe.
But I think it's like technically, so they had Kip Thorne, who has an office upstairs, won a Nobel Prize. I'm not going to dispute Kip Thorne. And I think what he did was, I think what he said was that like everything in the movie is like not provably false. And there's parts that are very accurate. So I think the simulations of the black hole that they did actually ended up in scientific papers because they had Hollywood money to do like really advanced simulations that normally us poor astronomers don't get to do. Yeah, I think if you fall into a black hole, you probably don't return to Earth, and you don't get to go into the Tesseract and talk to your daughter. Yeah, so you should treat your family well before you get sent to space.
Love is probably not a force that
yes,
that
yes,
goes
very powerful, but
universal and
doesn't talk.
Love, forgive me. I guess I'm
the Department of Energy would love to have love as a force
as
that you
a
could
force
harness.
that they could rely on.
Yeah, but despite that, I think it's a great movie.
It's a great movie, but no, I don't think it's based on true events. Okay, I promise somebody in the back. I'll get to you soon.
Yeah, just one on the electromagnetic spectrum. You were talking about by looking at the different frequency bands and seeing the different time of arrival across different wavelengths of the fast radio pulses. What causes that shift in the apparent speed of light passing through the gas clouds of the different wavelengths?
Yeah, so it's literally caused by the gas itself. So as light travels through any medium, it can be slowed down by the material that is between us and the source of light. So the process itself physically, if you want to look this up, it's called dispersion. And specifically radio waves are sensitive to dispersion through cold plasmas. So the gas or the plasma, as we technically refer to it, has to satisfy certain physical properties in order for this effect to occur. But essentially you have phase differences that arise as a function of frequency, and that is what gives rise to the time delays that we see. But it all arises from the so-called dispersion relation in plasma. So if you want to learn more about the physics, that's the key term to look up.
But strictly speaking, any kind of material, whether it's air or water or your glasses, has a different speed of light through that material. And we know this, it's usually justified as the index of refraction and why lenses cause light to bend, because both the shape as well as the fact that light is traveling at a slower rate in that medium than it is through air or through a vacuum. So it is you do have familiarity with this in our everyday experience instead of just in, deep space and the effects of dispersion. I said I was going to call on someone, but I forgot who it was. I'll get you in a second.
Thank you. Thanks. I had a different question about the FBRs, but now I'm more curious what each of your guys' favorite alien/space sci-fi movie is.
And before we get started with that question, if people haven't had an opportunity to look through the telescopes and want to, they'll be operating for only 10 more minutes, 12 more minutes. So get out there and check them out before they close down. But we'll keep going in here for a few minutes longer for the next half hour or so. Okay, so our question was, what are our favorite science fiction space films or books or just, okay. I mean, Interstellar is a good one. Interstellar is a really good one. I was just yesterday listening to the film score for Interstellar, which is just really powerful, very powerful. What
Star
other-
Wars. I feel like that's sci-fi. You gotta
Yeah.
give it to Star Wars.
It's true. Contact is very good.
I was gonna say contact.
The book is better, but the film is also very good. What else, guys?
If you've seen Pluribus, the show on Apple TV, the opening scene, sorry. Oh, cool. Yeah.
Oh.
The opening scene was filmed at the Very Large Array, which is one of the radio telescopes that Stella and Caitlin use.
I don't know.
Yeah, that was a nice scene because it was a slightly more realistic representation of what radio astronomers actually look like compared to Jodie Foster in Contact, where she's like literally listening with headphones, and that like never happens.
Notably, there's a film that I still haven't yet seen that was filmed at the DSA 110 site. So the site of that is a radio observatory just a few hours drive from here near the Eastern Sierra called the Owens Valley Radio Observatory, or OVRO, and it's near the towns of Bishop and Big Pine. If you're ever up there, you can see the radio telescopes from Interstate 395 or Highway 395. And there was a film that was filmed there called The Arrival, which has Charlie Sheen in it, and it was filmed in like 1985 or something. I've heard it's questionable, but it's good. Okay. So fun, maybe not good, but fun. Yeah. Okay.
Okay, so this may be, so when the radio waves are going from the FRBs and they're on the 300 billions of light years away, as they move through the gas, and then later on, as the FRB radio wave is still traveling towards Earth, what is the movement of the gas after it passes through that gas mean for like a modeling perspective? Like, do we understand how that gas moves in the 300 billion years since that point?
So you're saying the fact that we're receiving the signal now, but when it passed through that gas, it was many years in the past because it's so far away from us. Is this what you're asking? And how do we model that? It's challenging. So in the models, so I do some of this modeling. Usually when I'm modeling it, I'm using sources that are reasonably local to the Milky Way. So maybe the distance of the Andromeda galaxy, which by all astrophysics, by cosmological standards is quite close. It's only like a million, it's megaparsec. So it's like a few million light years away. And so then that delay isn't so substantial. The delay of motion from a couple million years ago to present is pretty small. But this is a challenge when you have these light cones where you're perceiving the motion that occurred on very long ago timescales. You definitely have to account for this finite speed of light and the fact that I mean, like for instance, when I'm talking to you, I'm hearing the sound from your mouth, and I'm seeing light that was scattered off of you in the past. It's a very short blip. It's like a picosecond between when you say something and when I see your mouth move. But I am looking at you in the past. And the farther away things are, the more we're looking at the past. And for the most part, we can just smooth over that because for the most part, it's just synchronous to us. But really, it is this effect. And so we're all doing this to some extent. When we see an image of the moon, it's 1 second in the past. When we see an image of Mars, it's 1.4. So it's like, it depends on where, yes, it depends on where it is in its orbit. If it's at opposition, it's like 3 minutes or something in the past. So yeah, all of these sorts of things. But yeah, we can account for that, but it's still in the early stages of us modeling these sorts of signals from very distant cosmological sources and accounting for that in our fluid dynamics models.
A fun fact is that light travels a foot every nanosecond. So
Foot every nanosecond. Okay, so picosecond was wrong. It's only, okay. So you're like 10 nanoseconds from when I say something and you see my mouth move to it happening.
Actually, I have a similar question. What he just asked is, like in the gas in the universe, how is the dynamics of it? Like what kind of time scale is moving around, and if you scan on the same direction, 1 day later, 1 month later, 1 year later, are they the same? Does those gas move around just like planet has a orbit, or do they have an orbit moving around? Or can you tell me what the gas look like?
Yeah, so that's a really great question. And the answer is unfortunately complicated. So it really depends on essentially what scale of the system you want to think about. If you want to think about gas that is moving, say, around the center of our galaxy, that takes very, very long time scales. What is the galactic rotation period? Do you remember? Anyone? This is such a good number.
Period for our Milky Way is about 225 million years.
So there you go. About 200 million years is how long it would take for a gas that's just moving around the center of our galaxy to complete a full orbit. But we do see some variability in interstellar space on much shorter timescales, on human timescales even, but happening at very, very, very small scales. So actually one of the techniques that I didn't talk about is that we can actually use pulsars to study interstellar gas structures that are about as large as our solar system. So we actually see like clouds of gas that are as small as our solar system in interstellar space. And we do see those very small gas clouds move across the line of sight to a pulsar over the time scale of roughly a month. So there are some cases in which we can actually see variability in interstellar gas on very short timescales. But then the timescales that are relevant to much bigger scale processes relevant to the evolution of the galaxy, its interaction with intergalactic gas, those happen on timescales that are orders of magnitude longer.
Okay.
Maybe to add to that, there's events like when stars explode that can really push gas to very high speeds. So some of the supernova remnants that are in pretty pictures that you've seen, the ones in our galaxy some of them are only a few hundred years old, maybe 500 to 1,000 years old. And those used to just be stars. So in those cases, gas can move very quickly, like to tens of thousands of kilometers per second. But most of the time, it's much slower.
We've got a question back here.
Thank you. And thank you guys for giving your presentation. I love it. To Dr. Coach Ocker, hi, my name's Naomi. I'm a special education middle school teacher. And so if you could explain your research to a 7th or 8th grade classroom in 1 minute, how would you do it?
That's hard. I think that's hard for all of us to do.
Is that a challenge to attempt to do so right now? I mean, I can try. So actually one of the things that I do in my free time is I am involved in this program called Letters to a Pre-Scientist, where you exchange letters with a middle or high school student, or sometimes even an elementary school student, a few times every school year. And so I've done this a couple of years now. The program actually covers schools all across the US and basically just pairs every student who participates with a scientist who then exchange letters with them. So I had to do something a little bit like this for this program. And what I said, I'm not sure if I liked what I said, but what I said is that I try to study the space between stars in order to better understand where we come from. And I do this using light that comes from other places in our galaxy. And yeah, that's basically what I said in 2 sentences.
Yeah, it's hard to get into.
It could be improved, I think.
Radio dispersion and all of these. Yeah, hard to get into the nuances.
Sorry, for a second, I forgot my question, but now I remember. Since radio waves are traveling such incredibly far distances and they could be so incredibly faint, when you're buying time for optical telescopes, I'm sure you're looking at very specific ones. Which ones are you usually trying to buy your time on? That's my question. Also, on the naming of telescopes, they really changed the book with the ELT on naming.
Yeah, that's true. The ELT, the extremely large telescope. It's being built currently in Chile.
Yeah, so we're lucky enough, especially at Caltech. Caltech probably has the most access to telescope time of any place in the world. And luckily for us, we don't pay for our telescope time directly. Like proposing for, well, somebody had to buy it. Somebody had to pay, and we were very grateful to those people. Right. And your question is, how do we know how much time to ask for, basically?
No, which do you choose?
Oh, I see. Yeah, so Caltech has access to the Keck telescopes, which are on Hawaii, on Mauna Kea. Those are two 10-meter telescopes. They're some of the biggest and most sensitive in the world. We also have access to the Palomar 200-inch telescope, which is in San Diego County, about a 2.5-hour drive from here. We were just there actually a few days ago. It's open to the public. If you haven't been there, I highly encourage you to go check it out. For 50 years, it was the biggest telescope in the world. And Stella and I at the Carnegie Observatories have access to the Magellan telescopes in Chile. Those are two 6.5-meter telescopes, which are not as big as the Keck telescopes, but the site that they're located is really exquisite. It's probably the best in the world. And so the conditions are great.
And it's in the southern hemisphere, so it has views of different stars than you can necessarily see. There's some overlap between their observing areas, but certainly you can see different stuff. But I think one of the main reasons that causes you to choose one telescope is not just the aperture and thus the sensitivity of that telescope, but also the instruments that might be on it. So some telescopes will have cameras for taking pictures in different wavelengths of light. Some may be in the infrared part of the spectrum, some may be in the visible part, some are maybe more efficient than others in the blue part of the spectrum versus the red part of the spectrum. But then there's also instruments like spectrographs that can disperse the color from white light, from starlight into the various different colors across the electromagnetic spectrum through the optical and the infrared. And then there's some instruments now that are increasingly being built, but they're pretty expensive to do so, which are kind of a combination of a spectrograph that splits the light into its component colors, as well as an imager that takes a picture. These are called integral field units or integral field spectrographs, because they take a picture, but then they have many different slices, many different images, where each image is giving you a different color of light from the light that's coming from that object. So you get some information about the spectra, which tells you about composition or temperature or the relative velocity of that object relative to you, as well as imaging information. So you have spatial information instead of just a single sight line, which you do in a traditional spectrograph. So I'd say that that's one of the main things that people factor into. I'm going to apply for time on that telescope because it has this really cool instrument that will allow me to do the science that I need to do as part of my proposal goals. Yeah. Oh, the young gentleman. I'll give you a third question. I won't give anybody else a third question, but.
Does dark matter obey the laws of physics like other matter does?
Keep them coming with these challenging questions. Does dark matter behave with the same physics as other matter does? Some of it.
Some of its gravity is the one that it obeys the most. That's actually basically the only way that we study it is it travels like other matter with gravity. So it clumps up, and that's why it can cause gravitational lensing, like some of the other questions were about. Does it obey other laws of physics? As far as we know, but we don't actually know.
We haven't collected a little chunk of dark matter locally so that we can study its properties. people are trying to do this, but it's really elusive. It's very difficult to catch. But yeah, Jeffrey's exactly correct. It appears the reason we think it exists is because we see anomalies in the gravitational field that we can't explain through visible stuff like protons and electrons and the stuff that we're all made of, and all of the things that we thought we knew existed are made of. And this appears to be not composed of that, and composed of something that only reveals itself indirectly through its effect, its gravitational effect on the stuff that we can see. It's like a ghost. You can't necessarily see a ghost, at least in the traditional thing, but you can see the sheet that's on top of the ghost. And so as the sheet moves around, you can figure out that there's something there that's moving the sheet. But if you take off the sheet, you can't see anything. Dark matter is kind of like that. That's a pretty bad analogy, but you get the idea.
Many people are hoping that laws of physics are wrong. We're not necessarily hoping, but many people, physics in studying physics, want to find new laws of physics that can kind of solve this dark matter problem.
Yeah, very good question. I promised this gentleman.
And I have sort of this burning physics question, and it might be in the research, but not quite publicly available yet. So it's really hard for me to find. It relates to refraction. Normally with refraction and reflection, you have some kind of medium, and then it either changes direction because of the phase of the light, or whatever thing is refracting or reflecting, or it could turn around and reflect. However, so I've been really interested in Dr. Judah Cohen's blog on the Arctic oscillation, and what he's saying is there are waves of planetary energy, and so this kind of gets into planetary science. The waves of energy, like in this winter, wave of energy came from, I think, Asia. It came up to the vortex, which is spinning, I forget which way. When that wave of energy is going a certain direction and then interacts with the spinning vortex, it actually reflects the energy back down towards North America, and that's what had a huge effect on our weather in the winter. So how does reflection happen in a spinning vortex when a wave of energy hits a medium that is a vortex that's actually spinning and not just stationary? So that is the burning physics question that I have.
Okay, so this is in the context that you're asking for atmospheric dynamics and atmospheric flows. And so there was some flow. I'm not familiar with the scientist you mentioned, Dr. Cohen, but there's some geophysicist or atmospheric scientist who measured a flow coming from the Arctic region or from the Antarctic region or from Asia that ran into essentially the polar vortex, and it reflected down onto North America. Okay. On the Earth, I mean, if somebody else wants to take this, I am happy to give it to you. I'll just say what I think is happening here, but I'm not an atmospheric scientist, but I do model fluid dynamics, so it's similar to this. On the Earth, we have a unique reference frame. We feel like everything is static here. You're sitting there, I'm sitting here. We feel like we're not moving at all, but of course the Earth is indeed rotating. And we can see this when we look up and we see stars moving across the sky, or we see the sun moving across the sky. It's not because they're moving, it's because we're moving. One consequence of this is that the reference frame on the Earth, because it's a rotating reference frame, suffers from something called the Coriolis force. And that means things, large-scale air flows or large-scale water flows that are traveling very large distances on the surface will move in a counterintuitive way to our intuition instead of in a straight line, because they're moving across a curved surface and because that curved surface is rotating as well. And this gives rise to things like hurricanes and the kind of vortical gas flows in our atmosphere that are generally associated with storms. I don't know the specific phenomenon that you're describing, but the counterintuitive motion that may be observed here is probably related to Coriolis effects, that it's taking it on a trajectory that you wouldn't normally expect it to take because of this strange reference frame in which we sit. I think that's the best I can do with that information. Sorry. You were waiting patiently before you went to the telescope.
So I wanted to ask for how do the pulsar emission physics or the mechanisms that we know how the emission process work, how does that inform how we characterize the surveys that we detect? Like how has that been a feature in your research?
I would have different answers to this question. So the physics of how pulsar emission works is still not very well understood. So there are some models for how it can be produced, basically from particles that get accelerated along magnetic field lines. Pulsars have very extreme magnetic fields around them. And so we think that that probably has something to do with the emission mechanism. I personally have not spent much time thinking about the emission physics because it really doesn't actually matter for most of the work that I do. It sounds counterintuitive, but the key property of the radio emission that matters for me is that it is coherent. So that means that the radio waves are emitted in phase. And that's a key requirement for using it as a tool to study all of the intervening gas. The propagation effects that I talked about, the distortions that the radio waves experience as they travel from the source to Earth, require that the emission be coherent when it first starts out. So that's really the only element of this picture that I care about, is that the radio emission is coherent and that it comes from a very compact source. So it essentially needs to look like a point source with respect to me, the observer. And that is related in a way to the emission physics, but those are really the two key properties of the emission that are relevant for me. I don't know if either of you want to expand on that.
I guess just specifically in the context of radio facilities. So there's a lot of phenomenology, a lot of different things, like pulsars can have different brightnesses, they can have different periods. Some of them spin like multiple times, like with a period of 1 millisecond. Others spin slower relatively at like 20 seconds or maybe even longer, who knows? And so again, this is sort of related to emission physics and such, but doesn't really depend on the exact details because we don't quite know the exact details yet. But because we know at least that there is this range of like pulsar periods or pulsar like refractive signals and such, we can sort of design our radio surveys to be as sensitive either to like a specific range of these like periods or phenomenology or to like a broad range. And so I think the DSA in particular is really trying to push for both, to be more sensitive and to be able to discover unknown, not previously seen behavior in like pulsars and such.
There's a couple questions online that I'll get to really quickly. One is, do radio waves also from distant objects have redshifts associated with the effects that the radio waves are passing through, and in the same way that other electromagnetic radiation does? And what can that tell us about distant sources in terms of their position or their velocity? I mean, I'm asking this, I could answer this, but I figured I'd ask you guys. What's the relationship between redshift and the signals from distant objects that's propagating through radio waves?
Yeah, so this is especially relevant for FRBs, which come from so far away that redshift dependent effects become relevant. So one of the effects that I talked about today was the delay in arrival times that we see at different radio frequencies. And so that in turn actually does have a redshift dependent effect when you start to look at FRBs that are very, very far away. So this gets into the effect of time dilation, and essentially that causes the delay that we see in the pulse arrival time to get stretched out depending on how far away or how far the redshift is of that source. I think probably someone can improve upon that answer.
I was just going to talk about a different radio observation, which is earlier there was a question about neutral hydrogen. And so neutral hydrogen, or mapping the neutral hydrogen in radio, or hydrogen intensity mapping, does take advantage of the fact that these radio wavelengths get redshifted the further away they are. So you can build radio telescopes on Earth that are specific to different wavelengths, and these different wavelengths or frequencies are basically corresponding to how far away or how redshifted these radio signals are. And so there are some radio telescopes that are looking for, say, like radio signals from like mapping the radio mapping the neutral hydrogen and radio from galaxies at like a redshift 2. And there's some radio telescopes that are looking for in redshifted radio emission from like the earliest possible time that radio.
The dark ages before stars even formed. And yeah. And then the final question from online was, do we use AI in our work, or are there other applications of AI in astrophysics that might be relevant?
So I'm just going to talk really quickly about FRB detections, because they happen literally in a blink of an eye, and we don't know where they come from, and we don't know when they'll go off. We have to constantly be searching in real time. And one of the reasons why we have to be searching in real time is because if we're just looking at the entire sky and collecting as much radio data as we can, the raw data rate, like in one day, is comparable to like the world's entire internet traffic rate in like a week or something like that. So that's not data that we can save and then search offline. It's data that we mostly have to search in real time, so that we don't have to save all this data. And so there are some physical laws that we know that these bursts have to follow, like dispersion goes like inverse frequency squared. And then we can use AI or like machine learned models really that are trained on what we know to be real astrophysical signals to differentiate from noise that just might go off, like maybe someone's cell phone went off near the radio telescope, or maybe an airplane passed by overhead. And so AI and machine learning tools are really crucial for us to do this real-time classification for FRBs.
I'll also just add to that, there is a very sad irony in this story, which is that we try to use AI to remove the interference, radio frequency interference that Caitlin talked about from things like cell phones, human-made signals, which are at the same radio frequencies of the astronomical signals that we're trying to detect. Now, right now, people are trying to put satellites into space at increasing rates. Those satellites produce a very strong radio frequency interference. People also want to put data centers into space. Those data centers, while potentially might be great for doing precisely the AI signal removal that I was talking about, would also generate a lot of radio frequency interference. So that actually, these satellite constellations, they're a real nuisance for the radio astronomy that we do.
And the optical astronomy.
Yes, for all astronomy.
Yeah, it turns out putting stuff in space in between us and the things we're trying to look at is kind of hard to see those distant things. They have started painting them black, but it's still an ongoing challenge. I mean, Elon Musk just proposed to the FCC to put 1 million data centers in orbit. And these data centers, it's not like a table. It's like the size of this building or larger, with enormous solar panels to power all of the computers on there. So then it's even larger, and that's all going to reflect and both block our view of the things, but also reflect light back down that's much brighter than the faint things, both in the optical as well as the radio and all the electromagnetic wavelengths. So it's challenging. It's a challenging problem. Astronomers don't want to be like no more progress in space. We got to do what we're doing here. But it needs to be a cooperative balance where there are things that they can do to mitigate that, like painting it different, a non-reflective paint can help a lot with things, but also just changing orbits. And it's a fraught business. And right now it's kind of the Wild West because there's not a lot of regulation on stuff that goes into space. I mean, maybe if they give us some radio telescopes, we'll let it ride a little bit. First question askers, you're a first question asker.
Thank you. Okay, if an FRB were to originate in the Milky Way, would we still see it in the radio wavelengths, or would it be shorter wavelength because it's closer?
See it at the same radio frequencies. So we got a little bit into this effect of redshift. So it turns out most of the FRBs that we detect that come from other galaxies, when they were originally emitted at the source, they were emitted at higher frequencies than we were actually observing. But as it traveled to us, it got redshifted down to lower observing frequencies, which happened to be the frequencies where we detected it and where we're also sensitive to galactic signals. But for that very reason, we actually think FRBs can be produced at potentially, frequencies that are 10 times larger than what we typically observe. But those just don't happen to be the frequencies we are observing now.
And we have detected an FRB from the Milky Way. Yeah, it was back in this happened in April 2020. And so I was part of the collaboration that detected it at the time. And it was already an international collaboration. So we were kind of already used to working on Slack, but now we were all stuck at home and had nothing better to do. And it was actually like we weren't supposed to detect signals from inside our galaxy and call them FRBs. But because this was so bright, it basically, we got lucky in being able to detect it and call it an FRB. And there was actually a little bit of a debate for if this originates from inside our galaxy, is it still an FRB or is it just an FRB-like radio burst? So there was a little bit of debate in the early days as to whether an FRB had to come from outside our galaxy to actually call it an FRB. But I think nowadays we call that one an FRB as well.
First time question askers. There's one. Okay. Just trying to spread the love here, get everybody.
Thank you. What is the average lifetime of a star, and how long and when a star explodes, how long does it last for? And when a star explodes, how long does the explosion last for?
Okay. Oh, I like this.
Yeah, this is a great question. So stars come in all shapes and sizes. The bigger the star, the shorter it lives.
Maybe not all shapes.
Okay, most of them are round. That's fair. That's fair. You got me on that one. Although there are simulations of the end stages of massive stars that are all wonky and lumpy.
Well, and I know the faster they rotate, we do see oblate
That's true,
spheres. So they look more like a hamburger than a sphere.
So not all shapes.
Okay, not a few related
shapes.
shapes.
Yeah.
Mostly
spherical.
Mostly
but they do come in all sizes. Well, many sizes. I'm not gonna. So the biggest stars that we know of are about 10 to maybe 50 times the mass of our sun, and those live very short, relatively short amounts of time, like maybe 10 million years or less.
Which sounds like a long time, but for a star, that's like.
Yeah, the universe is 13 billion years old, so 10 million years compared to that is like 1,000th of the lifetime of the universe. The smallest stars are about 10% the size of our sun, and those we don't know how long they live because we haven't ever seen one die. So they effectively live forever. It's the live fast, die young philosophy for stars. So if you live slowly.
Oh, yeah, this thing turned off at 10 o'clock here.
Oh, okay.
No, it's okay. I think, hold on, I'll fix this. We fixed this last time. It's like a hard set off to make sure we don't keep yapping is really the challenge. Forget how I did it last time. Well, okay. What I remember last time is it's still broadcasting. Do you see sound on yours? Okay, so the online audience can hear us. So just as long as people can hear us, then just.
Okay. Yeah, and our sun is probably going to live. I think it's probably roughly 8 to 10 billion years is what our. Maybe a bit long. Yeah, something like that.
We've got like another.
We've got another like 4 or 5
billion.
Yeah, and I think we're about 8 billion years old, something like that.
There we go.
Yeah, so our sun will live somewhere around 10 billion years. And when stars die, how long does it take? It depends on what you mean by die, and it depends on what you mean by how long it takes. So the explosion itself can be pretty quick, like on the order of, so this is, for massive stars, this is called a supernova. And usually a supernova lasts about, the actual explosion of the star can be super quick, like seconds, or maybe a bit longer, but short. But then what happens afterwards is the star loses its outer layers and gas gets pushed all over all at really high velocities of tens of thousands of kilometers per second. That causes a transient, so a spark of light in the sky, and that usually lasts somewhere about 3 to 6 months for most supernovae. We're actually overdue kind of for one that's in our Milky Way. The last one that we know of was, I think, 100 years ago or so, but that was like, we couldn't see it because it was behind somewhere else. And so if one goes off in the Milky Way that's not behind the middle, then we should be able to see with our naked eye for a few months.
But the comparison I'd make is when you see a firework go off, how long does the firework last? The explosion part is almost instantaneous, but then it expands and gets bigger and gets fainter over time. And so maybe after a second or 10 seconds, it continues. Even after it stops being visible to us, there's still that stuff that's still hot. You wouldn't want it to rain down on you. So if you had infrared eyes, you'd be able to see it for a much longer period. And it's the same thing with telescopes. So it depends, as you said, it depends on what you characterize as your explosion time scale, depending on its expansion and fading. Okay, since the room told us this is over by shutting off our microphones, that brings us to the end of our program. Please give a round of applause for both our speaker as well as our panelists. No more questions right now. But our next event of one of these will be in middle of July. I'll set the date very soon, probably about the Roman Space Telescope. And the next Astronomy on Tap will be in a week and a half on Monday, July 6th at the Doghouse. So maybe you'll be able to join us for that. Thank you very much. Bye. Oh, sure.